Hey everybody, we're going to work through a problem similar to what we did in whiteboard speed dating, and then we're going to go through using the kinematic equations to solve it. So with this problem, we have a car accelerating from 10 to 15 in 3 seconds, and then maintaining that speed. So let's go ahead and get started. We're starting with a speed of 10, we'll indicate that. We're going to a speed of 15, we'll indicate that as well. This is happening in a total time of 3 seconds. So we start at 10, we end at 15, constant acceleration for the purposes of this class. It's going to maintain this speed for another 5 seconds, so that's going to put us at a total of 8. Maintaining the speed means it's constant here. I think the easiest thing to do from here is to use the slopes to go from velocity to acceleration. So if we go ahead and we calculate the slope of the first segment, we have 15 minus 10 over 3, which will be 5 over 3. And of course, as a reminder, this is science class, so we will use decimal approximations. We get an acceleration of 1.67 meters per second squared. That's going to continue for that whole 3-second interval. After that, we see that we have zero slope. So we have the horizontal line, so zero slope for the remainder of the time frame. If you want to add this vertical dashed line, that's cool. If not, also fine. Over here on the position graph, then, for the first 3 seconds, we're going to show that the speed is constantly increasing. That means that this is going to need to curve in a parabolic fashion. Now, after the 3 seconds, it maintains a constant velocity. So whatever the slope is right at the 3-second mark, that's the slope it's going to need to continue with for all time. I don't currently, though, know what the value is supposed to be here, nor do I know what the value is going to be here at the end. We're going to need to do something else. So to do that, we're going to go ahead and use our other tool, which is to calculate the areas. I can take this velocity shape and I can break it down into a triangle and a rectangle. The rectangular piece is going to be 3 seconds times 10, which is going to give me a total of 30 meters for the rectangle. I also have this triangular piece. The triangle will be 1/2, 3 seconds, times the height. The height is just 10 to 15, so that's a total of 5. So we have 15 there divided by 2, gives me a total of 7.5. That means that in the first 3-second interval, we're going to travel the total of the rectangle plus the triangle, which is going to be that total of 37.5 meters. That's this location here. But the last part is easy, because the last part is just simply a rectangle. So we can take a look at that part. And we simply have the 5-second base times the 15-second height. So we have 5 seconds times 15 seconds. We work that out, and we get a total of 75 meters here. Now, this 75 meters represents the change. We're already starting at 37.5. So between here and here is that additional 75. So to get the total, we'll need to add that to the original 37.5 to get 112.5 meters. This is great. We've solved for all of the things. Now let's take a look at this in a slightly different way. I want to show you first that all of our formal kinematic equations, they come straight from these graphs that we've represented. So let's go back to the velocity graph and let's talk about how we went ahead and figured out position. To figure out the position of this piece here, triangle and the rectangle, we did the following. First, we calculated the rectangle. The rectangle has some initial velocity and for the height, and that happened for some amount of time. Then we had to add the triangle, which is 1/2 the base of the time times the height. Now, the height is the final velocity minus the initial velocity, which we indicate with v and v naught. This is great, but it's not what you're going to see in a textbook. So how do we get that piece? Well, if I want to talk about the acceleration, we know that the acceleration was just the slope, which was here. So we saw that acceleration is equal to the final velocity minus the initial velocity over the time. Do you see the connection here? We can multiply both sides by t, and then we can get this expression for v minus v naught. I'm going to take this at and sub it in over here. Now we're going to be left with x equals v naught t plus 1/2 t, and then at, which we can simplify as v naught t plus 1/2 at squared. This is the first of our kinematic formulas. There's a second formula that we're going to use all the time, and it's actually just a derivative of this one right here. Because if I take this formula and we rearrange it to solve for the final velocity, we're going to get the following, which is simply this, that the final velocity is equal to the initial velocity plus at. There's a couple of ways to get that. One is that we can rearrange this slope formula. The second is that you'll notice this is the form y equals b plus mx for the line that we have up at the top. You see that? We have a y-intercept at the initial velocity. So there's that v naught. And then v naught plus what? The slope of this line is acceleration. Oh, look, acceleration is in the place of slope. And then t is what's on the x-axis. These two formulas are our main two formulas that we will use. Now there is a third formula, and the third formula does this. You take the second formula and you rearrange that to solve for t. And then you take t and substitute it in to the first formula. When you do that, you're going to get the following formula. V squared equals v naught squared plus 2ax. The convenience of this formula, of course, is that this formula allows you to solve for velocities or distances without having to worry about the time piece. With these three formulas, we can solve any kinematics equation that we're asked, as long as we have 3 of the 5 variables. So let's go ahead and take another look at the same exact problem, but now from a purely mathematical or equation standpoint. So if you'll bear with me here for just a moment while I restructure these pages, and then we'll get started. All right, we're going to take the same exact problem, and we're going to take a slightly different angle on this problem. So here's the first thing you're going to do. I'm going to continue to encourage you to draw that velocity versus time graph. And here's why. The velocity versus time graph indicates to me that there are 2 segments of motion. That means that when you use the formula, you're going to need to use them 2 separate times in order to get the answers that you are looking for. So we have 15 meters per second at the end, and the beginning of this run, we're starting at 10 meters per second. Rearrange that so that works. So this graph indicates to me I'm going to use the formulas twice. So for part 1, we're going to be solving first for this area, this section right here. That's our first leg of the trip. First thing you're going to do is draw your kinematic chart. X, V naught, V, A, T, and we'll fill that in. We don't know the position. The initial velocity is 10. The final velocity is 15. We don't have the acceleration at this time. We do have the time of 3 seconds. Now again, I'll remind you, we have our 3 kinematics formulas, which are as follows. X equals v naught t plus 1/2 at squared. V equals v naught plus at. And v squared equals v naught squared plus 2ax. Now, something you'll notice is that acceleration is in all 3 formulas. That means if we don't have acceleration, that's going to need to be the first thing we find. We have no choice. So what we do is you take your finger and you cover up the variable that we don't need. In this case, we are not worried about x because we need to find a. So we go ahead and we do that, and we need to find a formula that has these four quantities, v naught, v, a, and t in it. And we can see that that is the second formula that we'll be using. So step 2 is you write down your formula. V equals v naught plus at, exactly as is. Then you can plug in your numbers and begin to solve. So we have 15 meters per second equals 10 meters per second plus a and the time of 3 seconds. And then we can go ahead and solve for a. You're going to notice this is the exact same thing we did earlier because we're basically calculating the slope. 15 minus 10 and then divide by 3. That's going to give me that 1.67 for acceleration. Fantastic. Now that we have acceleration, we can use any formula we like that has position in it to solve for position. So we'll go ahead and do that. I'm going to choose the third equation because I don't have to worry about a t squared in that equation. So we have the final velocity of 15 squared equals v naught squared, so 10, plus 2 times a times x. And that's what we're solving for, right? And we go ahead, we do the algebra of that, and you're going to get the same exact answer that we had before. So we have 15 squared minus 100 squared, 10 squared, which is 100. So we have 125 equals 2 times my acceleration, x. Go ahead and divide that out. And we get an x equal to 37.4. Now again, if we come back to our previous answer, that was what we got for our total answer here. There's our 37. All right, so we've now found the first chunk. And now we need to do it again for the second chunk. Now when you do it for the second chunk, here's what we need to remember. The final velocity from part 1 is going to be the initial velocity for part 2. So effectively, if we have multiple stages, you have a chain problem going on here. And so that will allow you to then go ahead and fill in the chart. Every section of a problem, you need to make a new chart and solve for all of the things in that chart before you can move to the next one. This is again why I really strongly recommend to let velocity versus time graph first, so you know what you're looking for and where you're going. And sometimes using the velocity versus time graph is actually going to get you your answer faster and more efficiently than doing it this way. You now have both ways to solve the kinematics problems, so you can try both ways on your homework and make sure that both answers check out. I know that this way is probably the way that feels really good to you, so make sure that you're also doing areas and slopes. Can't wait to work with you tomorrow.